Good morning, everyone. How are you all? So, today we're going to start with our new chapter, that is equilibrium. And when we talk about equilibrium, you people must be knowing or must be thinking what does exactly equilibrium means in chemistry. So I would like to tell you that chemistry in equilibrium, when we talk about chemistry, lot many things comes into the mind. We talk about equations, we talk about different live experiences, and we talk about different kind of reactions in this chapter. And we will be studying a lot many things which we can relate it with our life also. So let's first start with what new topic by relating it with the life. Now you tell me, what is equilibrium in our daily life? Let me give you two very important examples. One is in your junior classes, maybe in your senior also, you would love to go to the playground and do a kind of a swings and all. So in that swing, there is a kind of a swing which children used to love, but that has a typical kind of a balancing in it. I should use the word balancing. Now what does that mean? That means is you must have recall yourself, on one side one child used to sit, another side another child used to sit, and on that a balancing has to be done. Exactly, that's what is my thought, that you will be going to have a kind of a this. Yes, so this is nothing but seesaw. Clear? So when we are talking about this seesaw, I just gave you an example that it is just like if suppose you are having a child A sitting this side and a B sitting this side. Now this is a slant. Why this is a slant? This is a slant because this A is having a more weight, right? When I talk about more weight. But this might not be having that kind of a weight. But at one position, they are able to manage it. So it becomes like this. They are in a state where there is, you can say, no extra force or kind of any unwanted force is applying either on this side or either on this side. So they are balanced. They are simply balanced like this. Let me give you one more example. Most of the children must be driving a car, right? If suppose the front two wheels, one wheel is having a less air and suddenly it get puncture, what will happen? The car will become imbalanced. But when all the four tires of the car are in a proper inflated with air, they are balanced. There is no unbalanced force there. That is equilibrium. That is what we call equilibrium. We say we are balanced here. Clear? But this is what is static equilibrium. Static means it is at a one place only. But when we talk about chemistry, it is not like this. This you can take it when there is no zero state in the equilibrium. Clear? Means it is completely balanced. Let us go a little bit more about it. Now, in chemistry, when we talk about equilibrium, we mostly talk about reactions. So let us see, I am taking a reaction A changing into B. Now, what is equilibrium in this? Remember, in equilibrium, when I am again repeating, when I am saying that A is changing into B, means there is no external force at that particular position when they are in equilibrium. They are like this. No external forces applied on this. They are completely balanced. See, no opposing forces are there. They are in a balanced state. Even if there are two members and here it is only one member, still they are balanced. This particular state in our chemistry is known as equilibrium. Am I clear to all? I hope you all have understood. So let us go further. Now when we talk about this, what is this now? See, remember one thing. When I talk about A changing into B, now why I have used this kind of an arrow? And another is this. What does this means when I talk about these particular signatures? Remember this, the arrow which I am talking about here is, this means forward reaction, right? And if I am talking about this particular things, right? This means backward reaction. Now, what does these two word means? This means, here it is written rate of forward reaction. What does that rate means? Rate means speed. Speed with which that reactant is converting into an product. The same way it is coming back. Always remember one thing. When I used to go to my school, suppose my house is here and my school is here, and I'm using this particular path. Maybe the child living near to my house can use this particular path, right? It can be possible, na? Maybe the child can use this particular path, but when you want to go back, you have to follow the same path. That means it is in reversible direction. So here it is same, see, reversed, right? Means you have to follow the same path by which you have come. It is not like this that you are doing it in this manner, that you are coming up from here, from A to B, you are coming in this direction, but while going you are using this direction. No, then it is not a reversed direction. You cannot say the reaction is reversed. Reaction will not be reversed. So we have to keep this in our mind, that it is never like this. So this sign indicates us about equilibrium, that now my system is completely in equilibrium. Rate of the speed with which A is getting converted into B, the same B is getting converted into A. So we have to keep this in mind. Am I clear? I hope everything is clear to everyone, right? So let's move a little further. See, this sign is the most important. If suppose you are just writing A changing into B, this doesn't means your equilibrium. Remember this. This is not an equilibrium. This means only the forward reaction, not the backward. If you are writing in this way, this may B is getting converted into A, but not again an equilibrium. So this sign only tells us that the reaction is in equilibrium, and we are talking about those systems which are achieving an equilibrium or are either on the equilibrium. So the next thing is, now when we talk about chemical reactions, how can we say that a system is in equilibrium? Let's take an example. You must have studied this reaction. Acid plus a base gives you a salt plus water. Let's take an example here. I'm taking an example of HCl plus NaOH changing into NaCl plus H2O. Now see, already a salt is formed. It's the same table salt which we people eat. So can you take that table salt, mix it with water, which you normally must be doing when you're making a lemonade. Mix it with water. Is it getting converted into this? Acid and base? Never. So that means this is not a reaction which can be reversed if I'll follow the same things also. Am I clear? Next thing, when I talk about next particular thing, let's take more example here. One is this. Second, in grade 10 and even in 11, you have studied a simple reactions of your precipitations. Clear? Now, when I talk about precipitation reactions, I talk about is your this. Let's take this example here. BaCl2 plus Na2SO4. Now, this is a double displacement reaction. This will combine with this and this will combine with this. So, we form NaCl and BaSO4. Now, this is a white precipitate, right? Take that white precipitate, mix it with NaCl aqueous solution, you will never able to get these things. So that means this is also not an equilibrium. This is also not an equilibrium. So means these are just a simple chemical reactions which are going in only in one direction, that is forward, not are reversing back. Am I clear? Okay, so let's move a little ahead. See, when the process means one substance is getting converted into another but not reversing back. Am I clear? I hope. Let's move further. So, now let us study what are the types of reaction. Just I have classified two things to you. One means one is moving in the forward direction, one is coming back. So, when I talk about irreversible reaction means this reaction only. That NaCl when mixing with water, what it is giving you? NaCl aqueous solution, right? But it is not giving you HCl plus NaOH. Clear? Another example, let's see. If I am taking, let us reverse it. HCl plus NaOH gives you NaCl plus water. Now this reaction is only in this direction, means it cannot be reversed in anyhow, any condition you follow, but it cannot be reversed. I just told you, you are coming by this path. If you will follow the same path, then only it is reversed. Otherwise, it is not a reversible reaction. Clear? Let's move further. See, another thing, only in forward direction, this sign is very, very important for you. Clear? It cannot be converted. I just said only the reactants can be converted into products, right? But this thing cannot go back. Am I clear to you all? I just told you A can be converted into B. B cannot be converted into A back. This is not possible in the irreversible reactions. Clear? See, you must have seen one simple thing. When around 2 to 3 years back, many people have burned their currency just to avoid their black money, just not to show it to the prime minister accounts and all that, whatever. But the thing is, have they able to get that money back? Because they burn it. They just simply burn it so that they should not come into the eyes of the tax people. So same thing. That is not reversible. Once it is gone, it is gone. Simple combustion reaction. Take it. You are burning your carbon with oxygen and you are doing carbon dioxide. Are you able to collect this carbon dioxide and get it converted into this? No, you're not able to do it. That process will be completely different. Am I clear? So this is only a irreversible reaction. Now see, these all are irreversible reactions. Your neutralization, precipitation, combustion, redox reactions, you cannot reverse them until and unless certain conditions are completely reversed, but not the same conditions are reversed. Clear? Next, let us talk about irreversible reaction. Now, irreversible reaction, let us take N2 plus 3H2 gives you 2NH3. Now, they all are in gaseous form. Now, one thing I am here saying is this arrow. Now, what does that mean? Means that the conditions which you applied while converting this nitrogen and hydrogen into ammonia, this is an Haber process. There are certain conditions which we apply, which we will be studying in Lee-Chatler principle little afterwards. So, whatever the conditions we are applying here can be reversed in same manner and we can get back the reactants. So, reactants once converted into product can be converted back. So first condition is this arrow. Second condition, reactant can be converted into product, product can be converted into reactant. Now, very important thing, when they reach at equilibrium, what is happening? The speed is maintained, and another point, their concentration. When we talk about that reactant concentration is in equilibrium with product concentration. What does this mean? This doesn't mean if you are taking 1 ml is converting into 1 ml and at equilibrium they are same concentration. It doesn't mean same concentration. It means concentration is what your when we talk about concentration, concentration means is it is remaining constant, is becoming constant. Now, what does this means when I say it becomes constant? Means, take a simple example. I'm taking a container, I'm heating it. It has water in it and I'm completely covering it. Completely covered. What will happen? After some time, you'll able to see vapors here. Now, these vapors will touch the container lid and going to vaporize and condense back, right? At a particular point, you will feel that there is nothing happening in this container, but actually the reaction is happening. The liquid is getting converted into vapors and vapors are after touching that lid coming back into the container. That particular point where you feel there is nothing happening, but actually the thing happening is your equilibrium has been achieved. This means that concentration becomes constant, means reaction though happening, but there is no change which I can observe easily. Clear? So let us move further. See, in the both directions, sign is important. Now, this is very important, another thing. See here, when I talk about the type of reaction remains in the system even after a infinite length of time, means actually reversible reactions are slow reactions. They are not fast. See, you have done combustion. You taken carbon, you are burning and it immediately getting converted into this. So these are very fast reactions, irreversible ones. But when I talk about reversible ones, they take some time. One, they go in the forward, then they are returning back into the reactant side. So it's a quite a long process, not an easy thing that it will be very, very quick. Another, I just said reactants can be converted to products and products can be converted back to reactants. Clear? But in irreversible, it's never happening that from a carbon dioxide you get back this thing. This will not happen in irreversible reactions. Clear? Next, these are the simple examples of irreversible reactions. See, this sign is very, very important here. This tells you that the reaction is irreversible, not irreversible. If you'll make only this sign will indicate only irreversible. Now, these are the basic which we have just studied. Let us revise. Your formed product can react with each other to give original reactants. That what? Once it is getting converted, we can get back the reactant. But here that is not possible. In the next one, the complete conversion of reactant into product is not possible. Obviously, once it is getting converted into completely there, then it is very difficult to get back the thing. So some concentration change there, the reactant concentration keep on decreasing, and then we are coming it back. We will be studying this further in the chapter only when we will study ionic equilibrium. Now, complete conversion of reactant into product is possible. Yes, because I have just taken an example, carbon in the burning getting converted completely into carbon dioxide. It's not like that half of the carbon is left and then still after getting carbon dioxide, carbon is there. It's never happening. It's vanished means it's vanished. Next, I just said these are very fast, very slow. Both forward and reverse directions are possible. Only forward direction. Now, last point, law of mass action. We will be studying soon what exactly are these 2 points. Now, what does this diagram says? Now, I just said that concentration of the reactant and products remains same. Means if suppose I am having a product A getting converted into B and B is getting converted into A. I am talking about rate of the reaction of A is becoming equal to rate of a reaction of means A getting converted into B. Let's take it in this manner. Rate of forward reaction, A getting converted into B, and rate of backward reaction means B getting converted into A. Now, what does this mean? Iska, what does this exactly means? Means is, see, I just said the system is in equilibrium. I'm again repeating, system is in equilibrium. Why the system wants to be in equilibrium? The question comes is this. Why this whole chapter we are studying? Why a system want to come into an equilibrium? Just recall yourself about thermodynamics. Why a reaction occur? Why atoms react? Why any reaction is happening? To get the system into stability, right? System is in stability. When I talk about stability, what does that mean? In chemistry, what does stability means? Stability means minimum energy. What is minimum energy? This is minimum energy. G, what does we call it? Gibbs energy or Gibbs free energy. Free has been removed by IUPAC because it says nothing is free in the world. Everything is at some or the other cost. So Gibbs free energy, I'll give you a little bit recall of that. Suppose you are having you are at an age of 60, you have earned a lot. You are having a bank balance of suppose 100 crores, and suddenly you have a mind that I want to donate some money in some useful work, in any useful work. But at the same time, you feel if I'm going to donate all of the 100 crores to the people, then what my family will going to do? But still you have a feeling to do something good. So what you thought, let me donate certain amount to the people in need and let me keep certain part in my family. So you have secured 60 crores for your family. You are left with 40. Now you are using that 40 crores in some useful work. And that is the minimum energy you are having. So that is what is your Gibbs energy. Means the minimum energy which is available to do some useful work. I'm using the word useful work. Now, how does this is related here? See here. When I am saying a reactant 1 is getting into product, it is follow this reaction. Why this? See, progress of the reaction means when A is converting into B, some smaller amount of A is getting converted into B. It's not like suddenly the whole amount is getting converted into B. Then it will not be a reversible reaction. Then it will be an irreversible reaction. So small amount is getting converted. So after that, what happened? When it is gradually, the reactant concentration is coming down. Means if this concentration is decreasing, right? When it is decreasing, it is losing some energy. So there is a point you feel this is at the lowest energy, right? Finally, it is going back here. But when it is returning in the same path, we find out again that this particular point is having the lowest energy. That means in equilibrium, the system is attaining the minimum energy, and at that particular point your equilibrium is attained. Clear? So let us again recall it. Means that at this particular point where I'm talking about G is becoming minimum, I don't want to say that your completely G is becoming minimum. I say G is having the minimum possible value so that the delta G will become 0. Delta G is what? Change. Right? Change in delta G will be 0, but G is minimum because you have studied in thermodynamics. And if for any reaction you are calculating, this is the possible thing, right? So if this difference will be minimum as much as possible, definitely this value will become 0. Clear? So this is what is your equilibrium. See, the free energy is minimum. Delta G of the system is also minimum. Now, let us study little more about equilibrium. Equilibrium has two topics. Now, when I talk about it has two topics, we used to say the equilibrium is divided into two parts. One is ionic, another is chemical. Now, this chemical we will be studying first. Ionic will come to the second part. See, now in this also we have two different types, physical and chemical. Now, what does this means? See, physical changes. If I am talking about here, I am talking about physical changes. You must have seen if you'll get an ice at a room temperature, what will happen? It will convert into water. Right? Now, why I have kept a sign like this? Because it is reversible. Keep this water into the freezer, you will again get the ice. So, what have you done? When you bring it to the normal temperature, you are removing the change. When you are getting it reversed, you are returning it that particular change. The heat which it has achieved from the environment, you are taking it back. You are keeping it in the freezer. That's why it is reversible. Let's talk about chemical changes. Now, these are those changes in which we talk about ions taking part and molecules taking part. Clear? So, we will be studying here about these chemical equilibrium. See, when we talk about ice converting into water, that comes into a physical part. When we talk about chemical, we talk about molecules together participating. This is an ionic equilibrium. See, ions. This is the second part which we will be studying. There are certain reactions which you can call it as a reversible reaction. Now see here, I just said nitrogen converting into ammonia is the forward reaction. This particular symbol tells you that the above one tells you that it is a forward reaction. And here the below one will give you the reverse reaction which is happening here right now. The ammonia is getting converted. Same number of moles. There is no change. See. There is no change even in the number of moles. Here it is 1. Here it is 1. So there is no change. The same thing is happening. So this is a reversible reaction. Now, how to justify it graphically? Let's study that. Now, suppose I am having a graph here. Now, I have taken this. Suppose at time t equal to 0, when the reaction started, what will happen? There is no product, means product is 0. So, let's take value 0 here, right? And suppose nitrogen is having some value A and hydrogen is having some value A. Now, in a container, if I am taking nitrogen and hydrogen, is it possible that the moment I put hydrogen and nitrogen, they will combine and they will give me nitrogen? No, it will not be happening. It will take some time. Slowly 1 mole of nitrogen will get reacted with hydrogen, then another mole will react. So slowly and gradually this will happen. So think, at time after suppose 10 seconds, I find out, we are observing this reaction and we find out that something is getting subtracted from this concentration. Kuch to subtract hua. Then again, from here also the same amount is subtracted. Now when that amount is subtracting, where exactly it is going? It is going here. It is going it is going here. Sorry. It is going exactly here. Means whatever is subtracting, it is going inside this. So means according to this, you can easily judge. So see, after understanding this complete equation and data, you must have understood that some amount of reactant getting converted into product means something is getting reduced. The concentration of reactant is getting reduced. So what will happen? If suppose the reactant, this is reactant and this is product. The concentration of reactant is decreasing, means the concentration of the product is increasing here, right? So let us understand this concept through a graph. So when we talk about this thing, let's see, the product is 0 here and we are having some concentration of nitrogen and hydrogen at this particular place, and this is your reactant. So I just, and this is the progress, means speed of a reaction you can say, or rate of reaction, right? So understand, when your graph of this is coming below, the graph of this is increasing, but at a particular point they will merge together. Now this is your which reaction? When I'm coming in this is a forward reaction. See, the graph is decreasing. If I'll show you, see here. Here the concentration decreased, here the concentration decreased. Simultaneously the concentration is increasing here. The moment it is decreasing, it is increasing. But at a particular point here, they both merge. Now what do you mean by this merge? Means an equilibrium is attained. That is attained. Again I am saying, when your this nitrogen plus hydrogen is getting converted into ammonia, the concentration of this is increasing here. See, it is keep on increasing. Same way this is happening. See, this is going back. So this is a backward reaction and this is a forward reaction. So let's take it in another more elaborated value. See, initial concentration of your hydrogen and this is maximum. We have done in the graph like this. I am again making a graph here. See, here it is maximum, N2 and H2. Concentration is maximum. And concentration of ammonia, which I have written here as product, it is 0. Yes? Then concentration of this increases, means the moment it is increasing, see, the moment this is increasing, what will happen? The reaction proceed till the equilibrium is attained. This is also happening, this is also happening till the moment the equilibrium is achieved. And the concentration of N2 and H2 decreases at the reaction start. When this is increasing, this starts declining. The graph goes in the lower slope, not in the higher slope. And similarly for the backward reaction. Clear? Now, this is what? But there is a question. Is it necessary that the curve should meet at the point? No, it is not necessary. Because we used to draw the graph in a different manner also. Let me show you how. Sometime it happens, you might find that a graph is given to you in this direction, this manner also. Right? When the same point is achieved, this is also equilibrium. So not necessary that it should be meeting at the midpoint. It is not necessary. Now this is your backward reaction and this is your forward reaction. Reaction pattern is completely same, but the equilibrium is attained here when the points are similar. So this topic we will be starting in the next class. Thank you so much. In the next class, we'll cover up the doubts also from the previous topic. Have a nice day. Thank you.